My name is Mark Dufour. I'm a research fish ecologist with the USGS Great Lakes Science Center. Fish movement may impact management decisions. Therefore, there's a general desire to refine our understanding of fine-scale temporal spatial movements of yellow perch in Lake Erie. To date, most of what is known about yellow perch movements in Lake Erie comes from historical, external, and pit tagging studies which rely on recaptures to infer movement patterns. These studies' results have been informative but do not provide us with the resolution needed for management or to explain movements ecologically. Telemetry may be a useful tool in this regard. However, our first attempt at yellow perch on Lake Erie required some refinement. So our group has started a staged approach, beginning with smaller questions, with the hope of building towards a large-scale study. It's no secret that Lake Erie yellow perch management is challenging. It requires collaboration among multiple entities and combination of many different data sources. So how can acoustic telemetry help inform management? Well, the current harvest policies rely on three critical assumptions, including that there are 4 separate populations necessitating 4 separate management units and 4 separate population models. Also, the timing and location of fishery independent surveys accurately characterize the populations within these management units. And finally, the natural mortality is low compared to fishing mortality and equal across management units. Telemetry can help evaluate these critical assumptions by characterizing population movement between management units, the timing of these movements, and the potential sources of mortality. Prior to releasing tagged individuals, we carried out a series of short-term tagging survival studies and an external tag retention and survival study. For the short-term tagging survival study, we implanted dummy tags of different sizes over a range of different sized fish and held them in large cages for 48 hours. We tested capture methods like trap netting, bottom trawling, depth at capture, season, and the length of time fish were held on vessel. In short, what we learned was that tagging smaller fish with larger tags in warm water and holding them on vessel for longer periods of time resulted in higher mortality. We also learned that compared to trap netting, bottom trawling led to higher tagging related mortality in waters greater than 30 feet. For the external tagging retention and survival study, we found that external T-bar tags had the highest retention rates compared to other options and had minimal impact on survival over a 6-month period. Moving forward, we were fortunate to receive funding through the Great Lakes Fishery Commission for a pilot project, as well as contributions from the Ohio DNR, Ohio State University Aquatic Ecology Laboratory, and the Great Lakes Acoustic Telemetry Observation System to tag and release fish in Lake Erie's western basin. Our goals were to evaluate the post-release survival of tagged fish and evaluate the quantity and quality of data acquired from different tag types and receiver array densities. To accomplish this, we first bolstered the Western Basin receiver grid so that we could evaluate the number of detections and detection probability at different receiver densities. We also tagged fish with a set of tags varying in transmission power, transmission delay, and sensor types. In total, we tagged and released 158 fish, all of which were captured with the help of Ohio trap net fishers. Here's a snapshot of the spatial and temporal detection data from all available receivers between October 2022 and August 2024, spanning the range of tag battery life. The tagging and release location occurred at the yellow dots on each figure. The black dots represent receivers, and the lines connecting consecutive daily detection events for each individual fish. On the right figure, receivers were sorted from east to west on the y-axis and time on the x-axis. Some of the broad take-home messages from these plots are that we got a fair amount of movement data back, which is encouraging. Somewhat surprising to me was that most of the fish remained in the West Basin, with only 4 fish moving east of the islands region. And finally, the number of detected fish declined through time, which was expected. The first objective of the study was to determine if the quantity and quality of detection data changed depending on the tag type and density of receivers. To do this, we subset the receivers into 3 different arrays with an average spacing of 3, 7, and 10 kilometers. We can see from this figure that as we decrease the number of receivers, we decrease the resolution of detection data, which is not surprising. For this analysis, we also removed the high density tagging array around the release location because it was only deployed for a short period of time after tagging. We used 2 different InnovaSea tag models in this study, V7s and V9s. The tags varied in power, which is basically how loud the transmitted pulse is. Louder transmissions travel further in water. They also varied in transmission delay, which is the time between transmitted pulses. Some tags transmitted more pulses, and some transmitted fewer pulses over a fixed period. Finally, depending on the tag size and transmission settings, the estimated tag life, which is an estimate of the number of days the tag will produce transmissions, also varied. The larger V9 tags had substantially longer tag life, higher power, and transmitted an intermediate rate. One metric for evaluating data quality between tag types and array densities is to calculate the detection probability over the time at large. This provides an idea of how many days you can expect to hear a fish while it's swimming around. A higher detection probability means you should get a more refined picture of its temporal and spatial movements. To do this, we use detection data to determine how many days a fish was swimming around. Those are the blue dots for each of these individual fish. And then we counted the number of days that it was actually detected. That's signified by the red dots. We then plugged these values from each fish into a model and estimated detection probability for each tag type across array densities. Here we have the estimated detection probabilities on the y-axis for each tag type on the x-axis across receiver array densities in the panels. Not surprisingly, we saw detection probabilities increase for each tag type as the receiver densities increased. We saw the highest detection probabilities from the V9 tag model, which have a more powerful transmission and an intermediate transmission rate. Detections for this tag increased from 8%, which would be around detecting a fish 8 days out of 100 at large, all the way up to 11%, which would be like detecting the fish 11 days out of 100 in a 3-kilometer array. It's not a large increase, but it is twice the detection rate we saw from the V7D tag in the 10-kilometer array, which had lower power and less frequent transmissions. This suggests that if detection days are rare, then using a higher powered tag with more frequent transmissions and bolstering receiver arrays when possible may be beneficial, especially given the larger tags have a longer battery life, so you'll gain a longer picture of movements. Our second objective was to quantify post-release survival and characterize fates. We did this using temporal spatial visualizations, recapture information, and predation and temperature sensors from 2 of the released tag models. The predation sensor is interesting because it transmits a code when the fish is released. But if the fish is predated, the digestive enzymes within the predator's stomach will dissolve a polymer in the tag, causing it to transmit a different code that signals a predation event has occurred. Here's an example of the spatial movements of a fish which remained in the Western Basin and also remained active all the way to the end of its tag life, which was a rare event. We then use time to event analysis, which basically quantifies the number of tagged fish that are still active through time. Similar to detection probability, we evaluated survival based on tag type and receiver array densities. We were able to assign 6 different fates to fish in our study, including harvest, predation, active, natural mortality, tag-related mortality, and unknown mortality. Interestingly, although detection probabilities increased with receiver array densities, the proportions of assigned fates were similar. However, we were only able to confidently assign a low proportion of fates, as 65% of fish disappeared for unknown reasons. Also, we identified around 25% of fish that likely died due to tagging. Moving forward, we hope to increase our rate of fate assignments to known events and decrease the tagging-related mortality. We believe we can do this by increasing the number of sensor tags that we deploy, improve our communication with stakeholders in the commercial and recreational fishing communities, and improve our tagging and release protocols to reduce time on vessel and allow longer recovery times at depth. Before running the survival analysis, we threshold out the tagging-related mortalities because these fish stopped moving or disappeared within 2 days of release and would not be representative of the untagged population. The survival analysis provides us with a curve displaying the decrease in proportion of active fish through time. Here we have survival curves associated with each of the receiver array densities. One of the big takeaways from this study is how rapidly survival declined. In fact, at 270 days post-release, only 13% of the fish that survived tagging were still active in the West Basin. These types of independent survival estimates are useful for evaluating survival estimates generated in statistical catch-of-age models. Interestingly, although probability increased at higher density arrays, detection probability, there was no significant difference in survival. This suggests that although higher density receiver arrays may provide better temporal spatial resolution, it may be less influential if evaluating survival is the study's goal. We also evaluated survival based on the 3 different tag models and saw consistently higher survival from fish tagged with V9DT models. These tags had a stronger, louder signal, relatively frequent transmissions, and a longer tag life. This would suggest that tag characteristics like power and transmission delay are more important for characterizing survival than receiver array densities. One caveat is that we tagged a higher proportion of larger fish with the larger V9DT tags, which could be a confounding factor. This type of information is beneficial, as we can use it in future studies to determine how many fish should be tagged to ensure what some percentage of fish remain active during the study period. We've learned a lot during these initial studies and have applied those lessons moving forward. For example, we have an ongoing project in Lake Erie's Central Basin, and we've improved our tagging efficiency, moving fish quickly from the holding tanks to open water holding cages. We're also now using a larger, deep release cage that allows us to lower fish to a specific depth before letting them go. This, we hope, has been particularly beneficial in the Central Basin, where tagged fish have been caught at depths below 30 feet and are experiencing barrel trauma. In this video, you'll see that many fish appear stressed and unresponsive at the top of the cage on descent, but when we reach a depth of around 35 feet, they regain equilibrium and begin swimming normally. We're only using the higher powered V9 tags now, and most of those have some type of predation, temperature, or depth sensor to help us characterize fates on the back end. We're also externally tagging all fish and have created a flyer that can be shared with stakeholders to hopefully increase the number of reported harvests. The Central Basin Project has been supported by the Great Lakes Fishery Commission and the Great Lakes Acoustic Telemetry Observation System. A brief update on this project: we released 139 fish during spring of 2024. Nearly all fish have been detected over a short period of time, and we've seen surprisingly large movements towards the western basin and towards the eastern part of the Central Basin, as well as north from the tagging location. So far, a handful of fish have been predated and a handful have been reported and harvested, both from recreational and commercial fishers. But there is much more data to come in this study. Our ultimate goal is to facilitate cooperation on a large-scale study to evaluate assumptions used to manage Lake Erie yellow perch, including the number of populations and management units, timing and location of fishery independent surveys, and mortality rates. We're doing this by continuing to refine tagging and survey protocols. We're also continuing to gather more information from the Central Basin, and we're cooperating with partners on related yellow perch projects in Lake Erie. Many folks have contributed to this project, and I'd like to thank all those listed here. If you have any further questions or would like to discuss future directions of this project, don't hesitate to reach out. Thank you.